Chapter 12, Part 2 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook by the FAA. Performance and Limitations. Discussions of performance and limitations requires the definition of several terms. Accelerate stop distance is the runway length required to accelerate to a specified speed, either VR or VLOF, as specified by the manufacturer, experience an engine failure, and bring the airplane to a complete stop. Accelerate go distance is the horizontal distance required to continue the takeoff and climb to 50 feet, assuming an engine failure at VR or VLOF as specified by the manufacturer. Climb gradient is a slope most frequently expressed in terms of altitude gain per 100 feet of horizontal distance, whereupon it is stated as a percentage. A 1.5% climb gradient is an altitude gain of 1.5 feet per 100 feet of horizontal travel. Climb gradient may also be expressed as a function of altitude gain per nautical mile, or as a ratio of the horizontal distance to the vertical distance, 50:1, for example. Unlike rate of climb, climb gradient is affected by wind. Climb gradient is improved with a headwind component and reduced with a tailwind component. Figure 12-5. The all-engine service ceiling of multi-engine airplanes is the highest altitude at which the airplane can maintain a steady rate of climb of 100 feet per minute with both engines operating. The airplane has reached its absolute ceiling when climb is no longer possible. The single-engine service ceiling is reached when the multi-engine airplane can no longer maintain a 50 feet per minute rate of climb with one engine inoperative, and its single-engine absolute ceiling when climb is no longer possible. The takeoff in a multi-engine airplane should be planned in sufficient detail so that the appropriate action is taken in the event of an engine failure. The pilot should be thoroughly familiar with the airplane's performance capabilities and limitations in order to make an informed takeoff decision as part of the pre-flight planning. That decision should be reviewed as the last item of the before takeoff checklist. In the event of an engine failure shortly after takeoff, the decision is basically one of continuing flight or landing, even off airport. If single-engine climb performance is adequate for continued flight, and the airplane has been promptly and correctly configured, the climb after takeoff may be continued. If single-engine climb performance is such that climb is unlikely or impossible, a landing will have to be made in the most suitable area. To be avoided above all is attempting to continue flight when it is not within the airplane's performance capability to do so. Figure 12-6. Takeoff planning factors include weight and balance, airplane performance, both single and multi-engine, runway length, slope and contamination, terrain and obstacles in the area, weather conditions, and pilot proficiency. Most multi-engine airplanes have AFM, POH performance charts, and the pilot should be highly proficient in their use. Prior to takeoff, the multi-engine pilot should ensure that the weight and balance limitations have been observed, the runway length is adequate, the normal flight path will clear obstacles and terrain, and that a definitive course of action has been planned in the event of an engine failure. The regulations do not specifically require that the runway length be equal to or greater than the accelerate stop distance. Most AFM POHs publish accelerate stop distances only as an advisory. It becomes a limitation only when published in the limitations section of the AFM POH. Experienced multi-engine pilots, however, recognize a safety margin of runway lengths in excess of the bare minimum required for normal takeoff. They will insist on runway lengths of at least accelerate stop distance as a matter of safety and good operating practice. The multi-engine pilot must keep in mind that the accelerate go distance, as long as it is, has only brought the airplane under ideal circumstances to a point a mere 50 feet above the takeoff elevation. To achieve even this meager climb, the pilot had to instantaneously recognize and react to an unanticipated engine failure, retract the landing gear, identify and feather the correct engine, all the while maintaining precise airspeed control and bank angle as the airspeed is nursed to VYSE. Assuming flawless airmanship thus far, the airplane has now arrived at a point little more than one wingspan above the terrain, assuming it was absolutely level and without obstructions. With, for the purpose of illustration, a net 150 feet per minute rate of climb at a 90-knot VYSE, it will take approximately 3 minutes to climb an additional 450 feet to reach 500 feet AGL. In doing so, the airplane will have traveled an additional 5 nautical miles beyond the original accelerate go distance, with a climb gradient of about 1.6%. A turn of any consequence, such as a return to the airport, will seriously degrade the already marginal climb performance. Not all multi-engine airplanes have published accelerate go distances in their AFM POH, and fewer still publish climb gradients. When such information is published, the figures will have to be determined under ideal flight testing conditions. It is unlikely that this performance will be duplicated in service conditions. The point of the foregoing is to illustrate the marginal climb performance of a multi-engine airplane that suffers an engine failure shortly after takeoff, even under ideal conditions. The prudent multi-engine pilot should pick a point in the takeoff and climb sequence in advance. If an engine fails before this point, the takeoff should be rejected, even if airborne, for a landing on whatever runway or surface lies essentially ahead. If an engine fails after this point, the pilot should promptly execute the appropriate engine failure procedure and continue the climb, assuming the performance capability exists. As a general recommendation, if the landing gear has not been selected up, the takeoff should be rejected, even if airborne. As a practical matter for planning purposes, the option of continuing the takeoff probably does not exist unless the published single-engine rate of climb performance is at least 100 to 200 feet per minute. Thermal turbulence, wind gusts, engine and propeller wear, or poor technique in airspeed, bank angle, and rudder control can easily negate even a 200 feet per minute rate of climb. Weight and balance. The weight and balance concept is no different than that of a single-engine airplane. The actual execution, however, is almost invariably more complex due to a number of new loading areas, including nose and aft baggage compartments, nacelle lockers, main fuel tanks, auxiliary fuel tanks, nacelle fuel tanks, and numerous seating options in a variety of interior configurations. The flexibility in loading offered by the multi-engine airplane places a responsibility on the pilot to address weight and balance prior to each flight. The terms empty weight, licensed empty weight, standard empty weight, and basic empty weight, as they appear on manufacturers' original weight and balance documents, are sometimes confused by pilots. In 1975, the General Aviation Manufacturers Association, GAMA, adopted a standardized format for AFM POHs. It was implemented by most manufacturers in model year 1976. Airplanes whose manufacturers conform to the GAMA standards utilize the following terminology for weight and balance. Standard empty weight plus optional equipment equals basic empty weight. Standard empty weight is the weight of the standard airplane, full hydraulic fluid, unusable fuel, and full oil. Optional equipment includes the weight of all equipment installed beyond standard. Basic empty weight is the standard empty weight plus optional equipment. Note that basic empty weight includes no usable fuel but full oil. Airplanes manufactured prior to the GAMA format generally utilize the following terminology for weight and balance, although the exact terms may vary somewhat. Empty weight plus unusable fuel equals standard empty weight. Standard empty weight plus optional equipment equal licensed empty weight. Empty weight is the weight of the standard airplane, full hydraulic fluid, and undrainable oil. Unusable fuel is the fuel remaining in the airplane not available to the engines. Standard empty weight is the empty weight plus unusable fuel. When optional equipment is added to the standard empty weight, the result is licensed empty weight. Licensed empty weight, therefore, includes the standard airplane, optional equipment, full hydraulic fluid, unusable fuel, and undrainable oil. The major difference between the two formats, GAMA and the old, is that basic empty weight includes full oil and licensed empty weight does not. Oil must always be added to any weight and balance utilizing a licensed empty weight. When the airplane is placed in service, amended weight and balance documents are prepared by appropriately rated maintenance personnel to reflect changes in installed equipment. The old weight and balance documents are customarily marked superseded and retained in the AFM POH. Maintenance personnel are under no regulatory obligation to utilize the GAMA terminology, so weight and balance documents subsequent to the original may use a variety of terms. Pilots should use care when determining whether or not oil has to be added to the weight and balance calculations, or if it is already included in the figures provided. The multi-engine airplane is where most pilots encounter the term zero fuel weight for the first time. Not all multi-engine airplanes have a zero fuel weight limitation published in their AFM POH, but many do. Zero fuel weight is simply the maximum allowable weight of the airplane and payload, assuming there is no usable fuel on board. The actual airplane is not devoid of fuel at the time of loading, of course. This is merely a calculation that assumes it was. If zero fuel weight limitation is published, then all weight in excess of that figure must consist of usable fuel. The purpose of a zero fuel weight is to limit load forces on the wing spars with heavy fuselage loads. Assume a hypothetical multi-engine airplane with the following weights and capacities. Basic empty weight, 3,200 pounds. Zero fuel weight, 4,400 pounds. Maximum takeoff weight, 5,200 pounds. Maximum usable fuel, 180 gallons. 1. Calculate the useful load. Maximum takeoff weight, 5,200 pounds, minus basic empty weight, 3,200 pounds, equals useful load, 2,000 pounds. The useful load is the maximum combination of usable fuel, passengers, baggage, and cargo that the airplane is capable of carrying. 2. Calculate the payload. Zero fuel weight, 4,400 pounds, minus basic empty weight, 3,200 pounds, equals payload, 1,200 pounds. The payload is the maximum combination of passengers, baggage, and cargo that the airplane is capable of carrying. A zero fuel weight, if published, is the limiting weight. 3. Calculate the fuel capacity at maximum payload, 1,200 pounds. Maximum takeoff weight, 5,200 pounds, minus zero fuel weight, 4,400 pounds, equals fuel allowed, 800 pounds. Assuming maximum payload, the only weight permitted in excess of the zero fuel weight must consist of usable fuel, in this case, 133.3 gallons. 4. Calculate the payload at maximum fuel capacity, 180 gallons. Basic empty weight, 3,200 pounds, plus maximum usable fuel, 1,080 pounds, equals weight with maximum fuel, 4,280 pounds. Maximum takeoff weight, 5,200 pounds, minus weight with maximum fuel, 4,280 pounds, equals payload allowed, 920 pounds. Assuming the maximum fuel, the payload is the difference between the weight of the fueled airplane and the maximum takeoff weight. Some multi-engine airplanes have a ramp weight, which is in excess of the maximum takeoff weight. The ramp weight is an allowance for fuel that would be burned during taxi and run-up, permitting a takeoff at full maximum takeoff weight. The airplane must weigh no more than a maximum takeoff weight at the beginning of the takeoff roll. A maximum landing weight is a limitation against landing at a weight in excess of the published value. This requires pre-flight planning of fuel burn to ensure that the airplane weight upon arrival at destination will be at or below the maximum landing weight. In the event of an emergency requiring an immediate landing, the pilot should recognize that the structural margins designed into the airplane are not fully available when overlanding weight. An overweight landing inspection may be advisable. The service manual or manufacturer should be consulted. Although the foregoing problems only deal with weight, the balance portion of weights and balance is equally vital. The flight characteristics of the multi-engine airplane will vary significantly with shifts in the center of gravity, CG, within the approved envelope. At forward CGs, the airplane will be more stable, with a slightly higher stalling speed, a slightly slower cruising speed, and favorable stall characteristics. At aft CGs, the airplane will be less stable, with a slightly lower stalling speed, a slightly faster cruising speed, and less desirable stall characteristics. Forward CG limits are usually determined in certification by elevator/stabulator authority in the landing roundout. Aft CG limits are determined by the minimum acceptable longitudinal stability. It is contrary to the airplane's operating limitations and the Code of Federal Regulations, CFR, to exceed any weight and balance parameter. Some multi-engine airplanes may require ballast to remain within CG limits under certain loading conditions. Several models require ballast in the aft baggage compartment with only a student and instructor on board to avoid exceeding the forward CG limit. When passengers are seated in the aftmost seats of some models, ballast or baggage may be required in the nose baggage compartment to avoid exceeding the aft CG limit. The pilot must direct the seating of the passengers and placement of baggage and cargo to achieve a center of gravity within the approved envelope. Most multi-engine airplanes have general loading recommendations in the weight and balance section of the AFM POH. When ballast is added, it must be securely tied down, and it must not exceed the maximum allowable floor loading. Some airplanes make use of a special weight and balance plotter. It consists of several movable parts that can be adjusted over a plotting board on which the CG envelope is printed. The reverse side of the typical plotter contains general loading recommendations for the particular airplane. A pencil line plot can be made directly on the CG envelope imprinted on the working side of the plotting board. This plot can be easily erased and recalculated anew for each flight. This plotter is to be used only for the make and model airplane for which it was designed. Ground operation. Good habits learned with single-engine airplanes are directly applicable to multi-engine airplanes for pre-flight and engine start. Upon placing the airplane in motion to taxi, the new multi-engine pilot will notice several differences, however. The most obvious is the increased wingspan and the need for even greater vigilance while taxiing in close quarters. Ground handling may seem somewhat ponderous, and the multi-engine airplane will not be as nimble as the typical 2- or 4-place single-engine airplane. As always, use care not to ride the brakes by keeping the engine power to a minimum. One ground handling advantage of the multi-engine airplane over single-engine airplanes is the differential power capability. Turning with an assist from differential power minimizes the need for brakes during turns and the turning radius. The pilot should be aware, however, that making a sharp turn assisted by brakes and differential power can cause the airplane to pivot about a stationary inboard wheel and landing gear. This is abuse for which the airplane was not designed and should be guarded against. Unless otherwise directed by the AFM POH, all ground operations should be conducted with the cowl flaps fully open. The use of strobe lights is normally deferred until taxiing onto the active runway. Normal and crosswind takeoff and climb. With the before takeoff checklist complete and air traffic control ATC clearance received, the airplane should be taxied into position on the runway centerline. If departing from an airport without an operating control tower, a careful check for approaching aircraft should be made, along with a radio advisory on the appropriate frequency. Sharp turns onto the runway, combined with a rolling takeoff, are not a good operating practice and may be prohibited by the AFM-POH due to the possibility of unporting a fuel tank pickup. The takeoff itself may be prohibited by the AFM-POH under any circumstances below certain fuel levels. The flight controls should be positioned for a crosswind if present. Exterior lights such as landing and taxi lights and wingtip strobes should be illuminated immediately prior to initiating the takeoff roll, day or night. If holding in takeoff position for any length of time, particularly at night, the pilot should activate all exterior lights upon taxiing into position. Takeoff power should be set as recommended in the AFM-POH. With normally aspirated, non-turbocharged engines, this will be full throttle. Full throttle is also used in most turbocharged engines. There are some turbocharged engines, however, that require the pilot to set a specific power setting, usually just below the red line manifold pressure. This yields takeoff power with less than full throttle travel. Turbocharged engines often require special consideration. Throttle motion with turbocharged engines should be exceptionally smooth and deliberate. It is acceptable, and may even be desirable, to hold the airplane in position with brakes as the throttles are advanced. Brake release customarily occurs after significant boost from the turbocharger is established. This prevents wasting runway with slow, partial throttle acceleration as the engine power is increased. If runway length or obstacle clearance is critical, full power should be set before brake release, as specified in the performance charts. As takeoff power is established, initial attention should be divided between tracking the runway centerline and monitoring the engine gauges. Many novice multi-engine pilots tend to fixate on the airspeed indicator just as soon as the airplane begins its takeoff roll. Instead, the pilot should confirm that both engines are developing full-rated manifold pressure and RPM, and that the fuel flows, fuel pressures, exhaust gas temperatures, EGTs, and oil pressures are matched in their normal ranges. A directed, purposeful scan of the engine gauges can be accomplished well before the airplane approaches rotation speed. If a crosswind is present, the aileron displacement in the direction of the crosswind may be reduced as the airplane accelerates. The elevator/stabilator control should be held neutral throughout. Full rated takeoff power should be used for every takeoff. Partial power takeoffs are not recommended. There is no evidence to suggest that the life of modern reciprocating engines is prolonged by partial power takeoffs. Paradoxically, excessive heat and engine wear can occur with partial power, as the fuel metering system will fail to deliver the slightly overrich mixture vital for engine cooling during takeoff. There are several key airspeeds to be noted during the takeoff and climb sequence in any twin. The first speed to consider is VMC. If an engine fails below VMC while the airplane is on the ground, the takeoff must be rejected. Directional control can only be maintained by promptly closing both throttles and using the rudder and brakes as required. If an engine fails below VMC while airborne, directional control is not possible with the remaining engine producing takeoff power. On takeoffs, therefore, the airplane should never be airborne before the airspeed reaches and exceeds VMC. Pilots should use the manufacturer's recommended rotation speed, VR, or liftoff speed, VLOF. If no such speeds are published, a minimum of VMC plus 5 knots should be used for VR. The rotation to a takeoff pitch attitude is done smoothly. With a crosswind, the pilot should ensure that the landing gear does not momentarily touch the runway after the airplane has lifted off, as a side drift will be present. The rotation may be accomplished more positively and/or at a higher speed under these conditions. However, the pilot should keep in mind that the AFM/POH performance figures for accelerate, stop distance, takeoff round roll, and distance to clear an obstacle were calculated at the recommended VR and/or VLOF speed. After liftoff, the next consideration is to gain altitude as rapidly as possible. After leaving the ground, altitude gain is more important than achieving an excess of airspeed. Experience has shown that excessive speed cannot be effectively converted into altitude in the event of an engine failure. Altitude gives the pilot time to think and react. Therefore, the airplane should be allowed to accelerate in a shallow climb to attain VY, the best all-engine rate of climb speed. VY should then be maintained until a safe single-engine maneuvering altitude, considering terrain and obstructions, is achieved. To assist the pilot in takeoff and initial climb profile, some AFM/POHs give a 50-foot or 50-foot barrier speed to use as a target during rotation, liftoff, and acceleration to VY. Landing gear retraction should normally occur after a positive rate of climb is established. Some AFM/POHs direct the pilot to apply the wheel brakes momentarily after liftoff to stop wheel rotation prior to landing gear retraction. If flaps were extended for takeoff, they should be retracted as recommended in the AFM/POH. Once a safe single-engine maneuvering altitude has been reached, typically a minimum of 400 to 500 feet AGL, the transition to en route climb speed should be made. This speed is higher than VY and is usually maintained to cruising altitude. En route climb speed gives better visibility, increased engine cooling, and a higher ground speed. Takeoff power can be reduced if desired as the transition to en route climb speed is made. Some airplanes have a climb power setting published in the AFM/POH as a recommendation, or sometimes as a limitation, which should be set for en route climb. If there is no climb power setting published, it is customary, but not a requirement, to reduce manifold pressure and RPM somewhat for en route climb. Propellers are usually synchronized after the first power reduction and the yaw damper, if installed, engaged. The AFM/POH may also recommend leaning the mixture during climb. The climb checklist should be accomplished as traffic and workload allow. Figure 12-7. Level off and cruise. Upon leveling off at cruising altitude, the pilot should allow the airplane to accelerate at climb power until cruising airspeed is achieved. Then cruise power and RPM should be set. To extract the maximum cruise performance from any airplane, the power setting tables provided by the manufacturer should be closely followed. If the cylinder head and oil temperatures are within their normal ranges, the cowl flaps may be closed. When the engine temperatures have stabilized, the mixtures may be leaned per AFM/POH recommendations. The remainder of the cruise checklist should be completed by this point. Fuel management in multi-engine airplanes is often more complex than in single-engine airplanes. Depending upon system design, the pilot may need to select between main tanks and auxiliary tanks, or even employ fuel transfer from one tank to another. In complex fuel systems, limitations are often found restricting the use of some tanks to level flight only, or requiring a reserve of fuel in the main tanks for descent and landing. Electric fuel pump operation can vary widely among different models also, particularly during tank switching or fuel transfer. Some fuel pumps are to be on for takeoff and landing. Others are to be off. There is simply no substitute for thorough systems and AFM/POH knowledge when operating complex aircraft. End of Section 2 of Chapter 12.